Our next speaker will be Kenji Fukayua from Stony Brook, and he'll speak on equivariant Floer homology.
Thank you for introductions, and thank you for organizers to give me opportunity to talk here. So the main, maybe because this is JDG conference, I first mention a bit about JDG. I think the first paper I wrote was actually published in JDG. It was something like 33 years ago, so kind of 1/3 of the full history. And probably there are four papers, I think, probably published in JDG. But honestly speaking, all my papers published in JDG are on Riemannian geometry. And after I turned to gauge theory and to simplex geometry, I still do not publish any papers in JDG. It may be that recent paper have a bit lower quality, or but a possible excuse is that after I'm working on this simplex geometry, the paper I write is longer and longer. And I remember that something like 10 years ago, when we were working on this Lagrangian Floer theory papers, Yao kindly suggested us a possibility to submit it to JDG. But then when we finished it, we found it's something like 1,000 pages. And it's a bit too lengthy to publish in JDG. So it is finally published in international press, but not in JDG. So maybe something I need to try is to simplify the proof of simplex pseudo-harmonic curve so that it fits in the size of JDG. But anyway, so I want to talk about equivariant Floer homology, but I mean equivariant Lagrangian Floer theory. So what I want to consider this X omega. This is a symplectic manifold, and G compactly group acts on it, preserving symplectic structures. And what I want to consider this L is a Lagrangian submanifold and Z invariant. And that is the situations. And something I want to explain is the theorem. Is just there get some structures Mk Z that is a case tense product of equivariant cohomology of this L. And this is some so-called infinity structure. I'm sorry, I don't want to talk so much about these definitions because it doesn't play so much role in our in this talk. But this is the main statement. And one important thing is that this is compatible with this usual structure. So we have this structure. And this is not a non-equivariant versions of infinity structure, which we cook up in the book I just mentioned. And this diagram should commute. So this is natural map from equivariant cohomology to non-equivariant cohomology. So this is MKZ and MK. So this is one statement. So you can just do this equivariant versions. And the other statement is, the other is the case of have two Lagrangian submanifold. So you have this 2 L1, L2, which is G equivariant. You have this Lagrangian Floer homology. Actually, under some assumptions like unobstructedness. And this is kind of related to this equivariant cohomology of the intersections. And this is the kind of in a usual related to the usual Floer theory. And let me mention these kind of things studied by another people like Hendricks, Lipschitz, Zarkov, but they assume some conditions, and this theorem is incomplete generality. And and their approach is much more in a kind of category of algebraic topology, and our approach is much more topological. And but this is something like equivariant version. So I want to say a few words about why we are interested in this kind of things to cook up this equivariant story. And one main motivation I came to this is about gauge theory. So gauge theory is in the following type of problem in gauge theory. We consider this two-dimensional manifold, compact without a boundary. And we consider this space of flat connections. So that is the homomorphism of the fundamental group to say SU2 divided by conjugations. And there is a kind of old problem called Atiyah-Floer conjecture, which concerns somehow, in symplectic side, concerns some Lagrangian Floer theory on this singular symplectic manifold. So this is the singular symplectic manifold. And the problem I was recently interested in is this, in a gauge theory kind of question is related to this Lagrangian Floer homology in this singular symplectic manifold. And this is supposed to be related to some other invariant called instanton homology, which is a more gauge theoretic invariant. But one of the big problem, I mean, one of the biggest problem to study this problem is this guy is singular. So to study Floer homology for a singular manifold is never successful so far. So then there is an idea which goes back to. So this is the kind of project I'm working on. This Archibald-Daimi. And I just want to, so this talk is related only some small part of this. But anyway, so there is an idea which is due to Manuelisk and Woodwards. And also this is based on much even earlier work of this Webb-Bushman and Lisa Jeffrey. Is the following. So this is a singular. So the problem is if you want to study this Lagrangian Floer theory, but to study it in a singular space is extremely difficult. But then there are some spaces. Let me write it. I'll check sigma. This is a smooth symplectic manifold on which this SO3 acts. And there is some notion called a symplectic quotient. That also I don't want to mention because that doesn't so much play a role in this main part. But you have this quotient space. Then this is R of sigma. So you have this non-smooth singular symplectic manifold. But in place you can replace it by some smooth symplectic manifold with actions. And the quotient space is something you want. And then then something we want to do is just to just replace this Lagrangian Floer homology of this Lagrangian submanifold of this singular space should be equal to SO3 equivariant Lagrangian Floer homology on this smooth space. But if you want to make precise, you have to remove some divisor. I don't want to talk about it. So in place of studying this singular symplectic manifold, you can consider this smooth symplectic manifold. But then, of course, you have to work equivariantly with respect to this SO3 actions. So this is actually my main motivation to study this equivariant Floer homology. So our proposal is to study this equivariant SO3 Floer homology on this smooth symplectic manifold with something equivalent to gauge theory side. But today, I don't want to talk about this gauge theory things. Actually, last week, there was a conference in Simon Center, Stony Brook, and I talked about gauge theory side. But so today, I just want to explain what is the main idea to construct this equivariant Lagrangian Floer homology. And this is one motivation. And there are several other motivations why this equivariant thing is useful. For example, one corollary of this theorem is the following things. So if x, suppose you have this x omega, singular symplectic manifold with z actions, and suppose you have a Lagrangian submanifold, and it is just one z orbit. And L itself is G. So you have just one Lagrangian submanifold, which is exactly this G orbit. Then we can prove that the Floer homology of this L with itself is defined, well defined. This is one applications of this full story, and I say a few words why it follows from this diagram. And the theorem in I cooked up as Ota and Ono is that if you consider this something like M0 of 1, and this is something like a homology class of L, and is related to this well-definedness of Floer homology. Floer homology. And well-definedness is actually very important because the whole context of this book is to cook up some obstruction theory. So we just say that you have a series of obstructions that is 0, we can define Floer homology with some properties. But then, of course, if the condition is not satisfied, we don't get anything. So to have some conditions that this is non-zero, and this obstruction is 0, is important. Otherwise, the theorem is just empty. But then we consider this diagram. So we consider this diagram, and in case we take this is 0. So then this is a ground ring. So you have this commutative diagram, and we see how where each one goes, and it should be some element in equivariant homology of L. And in our case, L is G itself, so this is just rank 1. And then if you just go here, it gives some fundamental class of this L. So equivariant cohomology is just one rank, and you just go from equivariant cohomology to ordinal cohomology. Its image is just a fundamental class. And this implies that in our assumptions, the obstruction theory gives something like obstruction is some constant times this fundamental class. And this is exactly the conditions that the Floer homology of L with itself is well defined. So in our particular situations of this L is just one orbit, the cooking up this, you just construct this equivariant theory, it automatically means that L with Floer homology with L itself is well defined. So that's one application. And actually, this claim, this statement is actually used in several papers already. And we used it in a case when this is a toric manifold. And we wrote a series of papers in about toric manifold, and this is a kind of orbit of torus actions. And we use this fact that the Floer homology is defined. And we wrote the proof that of this statement in that particular case. But actually, the proof, honestly speaking, is very delicate. And it's one of the most difficult part of the proof we wrote in this series of toric papers. And I'm happy that we have another kind of proof, because this proof somehow put this statement in much better perspective. I mean, before the proof is kind of using very delicate argument, it's a bit ad hoc. So it's very dangerous. And sometimes there are and then all toric paper we wrote for 5 papers relies on this particular statement. So, but then we put it in this general commutative diagrams, and so we understand why it works in that toric case much better. And the proof is kind of much less ad hoc, because in our case of toric paper, we use a lot of special features, for example, user factor G is abelian, but and also one orbit. But then this commutative diagram works in complete generality, so the proof is much less ad hoc. And of course, there are several other cases that this kind of situation occurs. For example, if you have a symmetric spaces, non-compact symmetric spaces, the maximal compact group gives that kind of orbit. So you have a lot of examples that, and there are several people who use this statement already to have some example of non-commutative examples, and they calculate some Floer homologies. And actually, some of them just asked me, okay, can I use this statement in that case? And I replied yes, but honestly speaking, the rigorous proof is now available. Okay, so now this is the 2 applications. There are some other applications. For example, you see this Horry-Buffett and also some others project about this mirror symmetry, and they use this kind of things. In a sense, something like they use linear sigma model with group action is equivalent to non-linear sigma model. And this linear sigma model with group actions, you just go to homological mirror symmetry type context, is this equivariant Floer theory. And there are people like basically Chris Goodworth, and they study this kind of problems using so-called nonlinear sigma model. And but somehow there are several other ways, and also to study these relations, we have to start in a Lagrangian case. You have to start to hook up this Lagrangian Floer homology. So that's motivations. Okay, yeah. I mean, I always feel that just to do it in equivariant ways, it's sometimes a bit easygoing, but I try to convince you that it is not so much easygoing. There are some good reasons to do this equivariant theory. And then I next want to explain why this is not so much trivial. I mean, so the story to cook up this usual infinity structure is, as I said, lengthy, too lengthy to be in JDG. And equivariant version is somehow uses it, but you need some new problems. And maybe I want to first some new tool to to do everything in equivariantly. G invariant way. So I just want to introduce some new tool. So this statement may be of independent interest. So I just want to state one particular statement, which I found for this to prove this main theorem. It's a following. So let us consider this sigma z. So this sigma is a nodal curve. It means that you have a Riemann surface with arbitrary genus, which may have some double point. And z is a subset of this nodal point. It is disjoint. You have this so-called marked nodal curve. And the theorem I want to claim in this case is the following. So I will explain why this theorem is related to this equivariant story. But the theorem is there exists a unique deformation of this nodal curve parameterized by complexly groupoid. So, of course, I need to explain what I mean. But first of all, let me remind you that there is one most important case that this kind of thing is completely well known. It's a case when this curve is called a stable. Stable means that this automorphism is a finite group. So this is a very classical result by Green and Mumford. If you have a moduli space of all stable curves, then this moduli space is not so bad. It's a kind of obifold. It's just locally a quotient by some. It's globally some complex algebraic geometric object, and locally it's a quotient by Cn by finite group. But then the main thing is that here we don't assume that this is stable. So I mean, if you know something about algebraic geometry, then the moduli theory, in a moduli theory, stability is very important. It's introduced by Mumford many years ago. And he tried to study something like a moduli spaces. And he starts from stable objects. He can cook up some moduli spaces. That's a kind of general strategy which people in algebraic geometry worked out. And if you go beyond the world of stable object, then the problem of moduli is very much more difficult. And in algebraic geometry, people go further to cook up even more general thing like a stack, Artin stack, or something called the algebraic spaces. And then there is a kind of notion of moduli of such a non-stable object. And my feeling is that this theorem may not be new in that sense. I think that something equivalent to this theorem should be known in algebraic geometry. If you start from unstable marked curve, I think algebraic geometry knows some moduli such a thing, which is some kind of so-called Artin stack. So if you try to use their theory, probably if you try to kind of translate what they proved into differential geometry, probably one can prove the theorems. But something which I think says that this notion of regroupoid, and I will explain what it is later on. But of course, the notion of Artin stack is actually very algebraic geometrically object. They use a lot of representing functors and many difficult things, and I don't understand it so much enough. But then if we want to try to, since I want to use it with this analytic problem of holomorphic disks, like more transcendental problems, so I need to kind of translate this algebraic geometry language to differential geometric language. And then kind of a couple of months before, I found that this notion of regroupoid is exactly do that business. And I will explain what it will be regroupoid, but regroupoid is also somehow studied by many people in differential geometry, especially there are a lot of people near simple geometry working on this. So I thought that this theorem is known, and then I just try to find in the reference that there are people who try to do this kind of thing using regroupoid. So far, I don't know the reference, so probably this is new in that sense. So if you know about some reference, please let me know. I don't believe this is kind of, in that sense, very new, but it's a kind of refers of this differential geometric language, what algebraic geometry people are doing. So now this is a theorem, and okay, so now I want to say a few words why this kind of theorem is useful to study this equivariant Lagrangian Floer theory. By the way, this theorem is written in my paper, which is in the archive. Let's see where it is. Okay, so it is something like one of my papers, which this regroupoid is the title, so you can, if you are interested, you can find it. So now, the most the thing we want to do is just you can consider this kind of problems better. So this is a set of all sigma z. Maybe so. Well, Floer homology, you need a modular space of holomorphic disks, but maybe it is easier to explain for the Gromov-Witten theory. So I will consider this MGL alpha. So this is a sigma z u, and the sigma z is this nodal marked curve. And G is a genus. And the number of marked point is L. And U is a holomorphic map. Holomorphic. And we identify some relations. And we assume this stability. There is a notion called a stable map due to Kontsevich. And you, not this, but you include U, you assume it's stable. And then something we want to do is the following things. Suppose X has a G action, and the symplectic form is preserved, then we can take this almost complex structure so that G preserves almost complex structure also. So now G naturally acts on this KL and alpha. Then something like what we can do is just we want to find this fundamental class in a G-equivalent cohomology. For example, say in a cohomology, G-equivalent cohomology tensor L. So usual Gromov-Witten theory, we can just do it in a usual cohomology group or cohomology group, but we want to do it in a G-equivalent way. And that is somehow the problem with this Gromov-Witten theory. But in a Lagrangian Floer theory, you will see similar problems. Sorry, this is hard to use. Oh. Okay, now there are several things we need to do, but then to cook up these moduli spaces, what we use is the following. what we use is the following. So for each p in this moduli spaces of alpha, then we can represent its neighborhood of p as a kind of map C from S inverse 0 and S is a section, so UP is a orbifold, and EP is a vector bundle. So in a sense, we consider this modular space, and the problem is this is very much singular, and we kind of approximate these singular spaces. We realize these singular spaces as a zero set of certain map, and this map comes from some finite dimensional spaces. So you replace this infinite dimensional problem to a finite dimensional problem. And then there are a lot of tricks in algebraic topology. You can do the rest. But then the problem we meet is the following things. So we have this picture. This is called the Kuranishi picture. In a deformation theory of complex structure, Kuranishi found that somehow locally this deformation theory can be reduced to this kind of finite dimensional problem. But then what we want to do is just we want to do this finite dimensional reduction in a G equivariant way. So what we want is the following things. That is UP, EP, SP, CP are all G equivariant. So you want to kind of so the equation is this d bar u is 0. So we want to kind of find this spaces not only approximate this neighborhood by this S inverse 0, but all these approximations done preserving these G actions. Then and the rest is something like rather finite dimensional topology tricks, and it's not so much difficult. So now I want to do this kind of things. Then something we need to do is the following. Suppose that sigma prime, G prime, U prime is epsilon close, very close. What I mean by close is the problem, but I don't want to go into detail. You have this original thing. So this is P. Then I want to consider the equations. D bar U prime is 0. So this is an equation that this element is an element of this UP. UP should be a neighborhood of this P, but it is something like a solution. So this is the neighborhood of P in this modular space. But this equation can be bad, so I want to replace these equations. D bar U prime is 0 modulo some finite dimensional vector space. Maybe let me write this Q. So EQ. So if you just relax the condition a bit, then you get the transversality and you get finite dimensional approximations. So this is a story to make this finite dimensional approximations. But then what we need to make everything G equivariant is just one single relations. This E of Q should be somehow G equivariant. I don't want to say what this means. This is easy to justify these definitions. So if this kind of relaxing the equation, you can do it in a G equivariant way, then you can construct everything in a G equivariant way. But then something like you have to find a family of Q to this E of Q, which is has this equivariance property.
So you're not taking any finite local groups?
Pardon?
You're not taking finite automorphisms of the charts?
Yeah, I mean this is just equivalence classes. So I mean this should be invariant by the choice of both isomorphism of this sigma Q. Q is isomorphic to Q prime. Then of course this should be coincides by natural isomorphism. But not only that, we need to assume that this is G equivariant in this sense. And the main difficulty to do this kind of thing is the following. I think it's some kind of problem of linear PDV. We have similar situations. So what we need is just the following thing. So you have this unknown functions. I mean, this is the differential equations. But you consider this triple, sigma prime, G prime, U prime. But then to define this, I want to kind of identify sigma with sigma prime. So suppose you have this kind of spaces given in original sigma, then your equation, you have to transform it to this nearby sigma. Then the problem is your moduli problem, you both move this source curve and also maps. And when you move the source curve, you want to kind of identify at least some singular diffeomorphism, well, but actually outside singular point. So this is a kind of typical problem. You have some nonlinear equations, they have nearby solutions. You need to identify the source spaces. And the issue is that J equivariance is that we have to make this diffeomorphism in a sense as canonical as possible, so that we don't break this J equivariance by this choice of the diffeomorphism. So now I want to mention that in the case this sigma z is stable, so if this curve itself is stable, then we can discuss in the following way. We consider this CGL to this MGL. So this is a moduli of stable curve. Right? So you just consider this moduli of stable curve, which is defined by Durin and Mumford. Then this is a kind of fiber bundle. So you take this C infinity trivialization of this fiber bundle. That's always possible for the fiber bundle. Then this C infinity trivialization means that you have a nearby object, you have this diffeomorphism. So you can just use the fact that you have a universal family of stable curves to identify sigma prime with sigma, nearby sigma. So that is a kind of strategy we can use in the case this sigma z is stable. And the bad case is that is the following. So in this case, you can do it. This is not so extremely difficult. And what's nice is that all this identification is just used on this source curve. So it is nothing with this target space. So everything is G equivariant because G acts on the target space. However, the main cases that in the most interesting cases, point we have to study is just this curve is not stable. So as I said that we have a stable map, so that if you include this map, you get a stable object, but this sigma g itself may not be stable. So the problem is sigma g may not be stable. So in that case, we don't have this nice Durin for the moduli spaces. And so you can easily see that this identification has an ambiguity, which is exactly the automorphism of this sigma. So that kind of problem I think people meet in this nonlinear PD problem. You want to fix the coordinate of the equations, but the coordinate has some ambiguity. That makes things worse. So now the issue is that this may not be stable. So the way to resolve it is using this a bit strange universal deformations, which I mentioned by this groupoid things. So this is I think all I want to explain why this kind of universal family is useful to prove this equivariant problems. So I want to explain what this theorem means in this groupoid language. So I want to explain what is this Lie groupoid in complex analytic category. So what is Lie groupoid? So Lie groupoid is basically a category. So let me write G. Then it has object. So, but not only this, but this guy should be a complex manifold. So usually Lie groupoid is discussed in C infinity category, but you can just obviously change it to C infinity category. So you have a set of objects, but it's not a set in this case. It is a complex manifold. So you have a complex manifold which is a set of objects. And then you have this morphism. This is also a complex manifold. So this is a set of morphism, but it's a complex manifold. Then you have a two structure map, S and T. from this morphism of gay to object of gay. So you have this S and T. This is the following thing. So you have a phi here. The phi is a morphism, but phi is a morphism from S of phi to T of phi. So this is a set of all morphisms. So it has a source and a target. So this S and T is a map which assigns the source of this morphism and the target of this morphism. So that is phi. An important thing is that we assume that S and D is a holomorphic. You have a two holomorphic map which assigns source and the target. And actually, very important assumption in this regroupoid story is that both are actually submargin. S, T are both submargin. It means that, individually submargin. If you join together, it may not be a submargin. And I don't want to write down all the axioms because it takes too much time. But and another thing is that all phi maps phi assign phi to the inverse of phi. This is also holomorphic. So in a groupoid, as you know, that all morphisms should be isomorphism. So there are some other obvious axioms. For example, if you have this morphism of gay and you take fiber product of morphism of gay, and this is T and S, you can compose. So this is a composition of morphism. This means that you have a phi and psi, and the target of T, phi is equal to source of psi. So you can naturally compose. And the assumption is that this composition is a holomorphic map. So you have several other axioms. If you just rewrite all the axioms on this category to this language, all the things is just holomorphic. Other than that, the same argument are the same. For example, there's a map which assigns each object to the identity object, and that map, that is also holomorphic. Okay, so this is the regroupoid. And I'm sorry to explain, I had not enough time to explain the morphism of regroupoid, but you can easily guess, right? You have two of this kind of regroupoid. You have a notion of functors. Functor is just an object correspond to object, morphism to correspond to morphism. And in this case, we assume all this part of the functor is actually holomorphic. So that is a holomorphic morphism. Then something I want to explain the following things. So I want to explain that this notion of regroupoid you can naturally use to study the notion of deformation of the complex structure. So you have this G is a complex regroupoid. Then I want to define C to G is a deformation, a family of complex variety. Complex variety parameterized by G. So in this language, and this is actually very easy, so that's why I want to explain. So you have this F. It's a functor. So they both are regroupoid, which is complex in our sense, complex analytic. And this functor is also complex analytic. And only one extra axiom is the following. You consider this morphism of C, and then you take this morphism of G, I have this target map, and you take this, this is F, sorry. And this is target map, you have this object of C, and you take this object of G, then you have target map, you have F. And the condition is that this is so-called Cartesian. It means that morphism of C is a fiber product of this object of C over this object of gay, morphism of gay. So this is and the same for S. So this is basically the only extra condition that this is a deformation of complex manifold. So maybe this is maybe I need to explain why it is. So the reason is very easy. So suppose we have this any x in an object of this gay, then you take this F inverse x, which is a subset of this object of C. So this is a complex variety. Right? So you have a family of complex variety parameterized by this object of gay. So that's one thing you get from this maybe I need to write from this axioms. But then something more important is how this morphism do. So suppose you have this phi. So So you have this x and y, and you have a phi. So phi is a morphism in G, and this t of phi is y, and s of phi is x. So it's this y. Then we consider this. So let me write it a bit longer. Let me write it phi. Then we consider this f inverse x, and then you take this f inverse phi and f inverse y, and this is all f. And what we know is that actually this is isomorphism. This is exactly the fact that this diagram is Cartesian. You have one object here which goes here, so the fibers are isomorphic because this is the fiber product. So it means that you have any phi which is a morphism from x to y, it automatically induces an isomorphism from f inverse x to f inverse y. So you have a kind of family of complex variety parameterized by the object, and you have any morphism, then it corresponds to some isomorphism between fibers. So this is something like a moduli problem are supposed to do. So you have a notion of this Lie group point, complex Lie group point, then you can naturally find the notion of the family of complex variety parameterized by this Lie OB4. But then I don't want to say the next, but somehow you can just use this language to say the kind of family of nodal curve parameterized by this Lie OB4. So you have some complex Lie OB4, so that the family is this in this sense. Is a family of nodal curve. And the claim of this theorem says that if you just consider this kind of theory of deformations, then it's always universal deformations exist. And I think I have just 5 minutes. So I want to explain one example of this universal family, which is which shows something what I am doing here. So we consider this particular simple curve. We have one S2 with 3 marked points, and you put this one S2 here. So you have this singular nodal curve of genus 0 with 3 marked points. And this is a typical example of unstable curve, because the automorphism of this curve contains this automorphism of this S2 with 1 point. So there is a non-compact group of automorphisms. So this is the sigma Z. And then let me think, what is the moduli of this kind of picture? And the moduli is something like, so the moduli of this guy, of this singular guy, is a complex one-dimensional. Because you have this has a no moduli, right? Of course, S2 with 1 mark point has no moduli. But you have a 4 point here, 3 marked points plus 1 nodal points. And S2 with 4 marked point has a complex one-dimensional moduli. So this is a moduli of this configuration is complex 1 dimensions. But then, of course, in the moduli theory, you have to kind of include the curve which resolve this singularity. So you have this singularity. Then you have an extra parameter rho. No, this means that you have this xy is 0 is performed that xy is rho, right? So this is a double point. So you change double point. So you have another rho which is maybe contained in this small disk. So total moduli space which deforms this guy is this complex one parameter which deforms this configuration plus another complex parameter which resolves this singularity. So your picture is something like here. You have this S. So S is this guy, moduli of this singular object, and you have everything else that is bigger dimensions. And in total, you have this complex two-dimensional things. But then, if you think a bit carefully, you will observe the following things. If you consider 2 points, xy, which is not in S, then actually x is isomorphic to y. Because if you resolve this singularity, you have this kind of situations. Then this is a S2 with 3 marked points. Of course, there is no moduli at all. So this is why this unstable curve is very bad in the moduli theory. You have this in the center, you have two-dimensional honest moduli spaces, so that each object are actually different. But you go away, everything is just isomorphic. So you have just one point away, and the central curve is big dimensions. So you just consider the set of all isomorphism classes. You have a very bad non-Hausdorff spaces. That's why people avoid this unstable things in this business. However, if you just regard this four-dimensional things as a set of objects of our category, then you can include this morphism so that this gives a nice universal family. So what is this object? So let me take this fourth thing as of z. You have this x, y of z. Then we can just take this morphism. It's like a g, x, y. It's just set of phi, which is something like a phi. So you have a whole set of biholomorphic map. So Z of all biholomorphic map is just some set. So we take this guy, and we take this union of gxy, and this is the morphism set of our G. And we have a natural map which goes to object of Z. It just assigns this to x and y. So something what is interesting is that first of all, this G of x is behave very bad when you move x and y. So how it behave? And for example, if x is not in this singular set, and x is different to y, then this G, no, I'm sorry. If x, y are not in a singular set, then gxy is 1 point. And if x is C and x is not equal to y, then this guy is empty set. And if x is y and in a singular set, this is S, sorry. Then gxy is 2 dimensions. So let me remind you why it is. So suppose you have 2 points which lies on this outside of this S. As I said, they are biholomorphic. They are S2 with 3 points. They are biholomorphic, and this biholomorphic map is unique. So this set of morphism is just 1 point. And if x is the singular point and y is not singular point and y is different, then there is no isomorphism. Then the last case is that if x and y are both on this singular set and it's equal, then you have an automorphism, which is an automorphism of this S2. So you have this phenomenon. And this G of x, the set of morphism, is not so much stable. It jumps. It rather badly jumps. But then if you just look this fourth set of this G of x G, and then you find the following things. If you consider S from morphism maybe T, from morphism of this G to this object of G, then the fiber is something like 2 dimensions. And more important is that there is no jump. So this morphism set is a kind of a bad jump, but if you fix this target space, then you consider all the morphism to that target, then the fiber is just something like locally constant. You can see from this, because in case when your x is in the singular set, then of course if the y is also x, then there are 2-dimensional things. So the set of all morphism which goes to x is 2 dimensions. But if they go outside, then you have a full set of this of outside of S, which is again complex 2 dimensions, which is isomorphic, and the morphism is unique. So regardless whether x is in a singular S or not, the fiber is always complex 2 dimensions, and you can cook up the complex structure on this full set of the morphism, so that this is actually a S, T and S are submargins. So that is this situations. So you have this both kind of moduli and automorphism behave bad, but you join together, you have some nice phenomenon. And the theorem just claims that if you include any more complicated configurations of this unstable curve, you can do the same business. And I don't say so much about why this is useful. In a sense, this means that the ambiguity of this parameterization of the curve It's just parameterized by the fiber of this map. So the ambiguity to parameterize your source curve is not unique, but it's parameterized by some nice family of manifold, which is locally constant. So it is much nicer than just a kind of jumping phenomenon. And you can use this together with certain maybe center of mass Riemannian trick to get this equivariant things. Okay, so now I stop here. Thank you very much.
Any questions?
In the context of mirror symmetry, the non-abelian equivariance action seems to be related to the abelianization modulo y group action. Is there any hints of this in what you're doing?
I think this is just kind of basic to define something. But once you have this kind of things, you can compare G equivariant Floer theory and maximal torus equivariant Floer theory plus wide group actions. So probably one can try to prove that kind of statement using this language. But I didn't. Yeah.
Any other questions?
So do you have the equivariant closed method, open closed method?
Pardon?
Equivariant version of the open closed.
Open close. Yeah, I believe so from this kind of ways, you can do most of the things in a parallel way in this equivariant setting. But I mean, yeah, how to write everything. But